Alright, so in this video we are going to be doing an Algebra 1 basic review, and this video is going to be about polynomials. Let's get started. So we're going to get started. When you have polynomials, or when you're multiplying binomials or polynomials, you probably have something like this. I'm going to give an example of binomials. I'm going to start off with a plus b and this is a product of binomials, and when we expand this, we can use distributive properties. So the way we're going to expand this is we do a c plus d plus the second term, everything else in the parentheses, and now we can just use some more distributive property, ac plus ad plus bc plus bd, and this is just the expanded form of these binomials. So that's how you would expand binomials. So I'm going to give an example here, and I want you to expand it and see your results. And solve that. Solve that. And yeah, I want you to solve those and tell me your solution. Alright, so let's start with the first one. So over here, we multiply a, that's a squared. This is minus ab. You move on to b. b multiplied by a, that's plus ab. And then we have b multiplied by b, that is, we have a negative b over here, so that's minus b squared. These cancel, so we have a squared minus b squared. Now let's go over here. This is 5 minus 4 multiplied by 5 plus 4. Well, 5 minus 4 is 1, and 5 plus 4 is 9. Now notice something cool here. What's 25 minus 16? I want you to compute 25 minus 16. Notice how both of these are perfect squares, and it's 5 squared minus 4 squared. And these terms cancel, as we did over here. Now we're moving on to a factorization. This is the difference of squares factorization. The difference of squares factorization says that when we have a minus b times a plus b, that's equal to a squared minus b squared. And this can be used for any difference of squares. We can use it 5 squared minus 4 squared can be factored as 5 minus 4 and 5 plus 4. And this can be computed pretty easily. This is 1, 5 plus 4 is 9. So the answer is 9. And that's how you can use difference of squares to compute difference of squares. The factorization to compute difference of squares. Now before we move on, I'm going to do another polynomial expansion thing. X plus y x. And expand that and expand this. I also want you to expand these polynomials. So expand both of these polynomials and see what you get. Alright, so I'm going to go ahead and expand the first one. I'm going to expand it down here. We have x times x squared, that gives us x cubed. And then we have this term over here, negative xy times x. Well, we have a negative x multiplied by x, so that's negative x squared y x squared, and then we add on the y, and then we have plus x y squared. Now we move on to the y. We have plus xy squared. We have minus y squared x plus y cubed. Now notice, we have negative x squared y, negative y squared x. Where's x squared? Well, this is 2x squared. 2xy squared, to be more precise. And then we have these terms. This can be written as 2xy squared minus 2xy squared. So all of these terms essentially just cancel out. And we're left with x cubed plus y cubed. Another interesting result. We have a sum of cubes. Let's expand the bottom part. If you've noticed, we have x cubed in the first term, multiplied plus x squared y plus xy squared minus x squared y minus x y squared. It's minus xy squared minus y cubed. X squared y minus x squared y cancelled. Xy squared minus xy squared cancelled. We have x cubed minus y cubed. So we're going to bring our eraser. X cubed minus y cubed. Let's take a look at our results. Sum of cubes, difference of cubes. These are the two factorizations for the sums and difference of cubes. That's how you would do that. Now, let's look at something different. I want you to go ahead and expand a plus b squared. See what you get. Now, this is just a plus b multiplied by a plus b squared. This is a plus b squared, same thing. Now, let's expand our binomials. That's a squared plus ab. We have b times a, which is just ab, plus ab plus b squared. ab plus ab, that's 2ab, a squared plus 2ab plus b squared. That's our expansion. Now I'm going to give you a challenge problem. Spot why this is true and how you can expand this without even going through all of this. Spot what we're doing here. I want you to spot what we're doing here. Alright, so we take the first term a, we squared it. Now we have this 2ab term. Well, the product of the terms in the binomial is ab. We multiplied the product of the terms in the binomial by 2, so 2ab, and we just squared the last term. But is this true for every single product of binomials? Well, we're going to have to find out. Let's place some values in a and b. So I'm going to place some values in for a and b. So I'm going to place a 2 and a 1, and I'm going to square it. Now, if we're doing the same thing here, we should get 2 squared, and we should get the product of the terms in the binomial multiplied by 2 plus 1 squared. That's b squared. But let's actually expand this out and see what we get. Let's see what we get. 2 times 2, that's 4, plus 2 times 1 is 2, plus 2 plus 1. This is equal to 4 plus 4 plus 1. Notice what we did. We squared the first term, 4. Product of the terms in the binomial is 2. 2 multiplied by 2, that's a 4. And then we squared the last term, 1. 1 squared is just 1. So we see it is coming to be the same thing. And we've in fact proved it here with the expansion of this. So we know that this is another factorization and that this can be factored into this. And this is a useful expansion, squares of binomials. When you're squaring a binomial, you take the first term, you square it. Now for the middle term, you're going to take the product of the binomials, ab, and multiply it by 2 to make 2ab, and then you square the last term, b. In this case, that's what we did. We squared the first term, 2. 2 squared is 4. 2 times 1 is 2. 2 times 2 is 4. And then we squared the last term, 1 squared is 1. So that's basically what we did there. Now, let's change things up. Now, we're going to talk about quadratic equations. Now, quadratic equations are in the form ax squared plus bx plus c. Essentially a type of polynomial equation that can be solved using the quadratic formula, minus b plus or minus root b squared minus 4ac over 2a. And this formula is referring to the a over here is the a over here, the coefficient of the quadratic term over here. So in a quadratic, this is the quadratic term. This is your linear term. And this right here is a constant term. So that's the parts of a quadratic, and you just plug your values in and you're good. So that's how you would solve any quadratic equation. Now I'm going to give a couple examples. And x squared plus 2x plus 4 equals 0. Solve the quadratic equation. Now I'm going to use quadratic formula minus, I'm going to put the quadratic formula up here. Now in this case, the coefficient of the quadratic term is just 1x squared. So we don't need this a. So in the b is 2, so we have minus 2 plus or minus b squared, b is 4, 2 squared is, b is 2, 2 squared is 4. Now we have minus 4 times a is just 1, c is 4, and negative 4 times 4, that's negative 16. And we have negative 4 times 4, and then over here we just have 2, because 2 times 1 is 2. Now let's compute this. This is negative 2 plus minus Now 4 minus 16, 16 minus 4, 16, 15, 14, 15, 14, 13, 12 is going to be negative 12 over 2. Now notice how this is the square root of negative 12. Now how can we express the square root of negative 12? Well, square root of negative 12, that's where imaginary numbers come in. Now the square root of negative 12, how can this be written? Well, if you don't know, I is equal to the square root of negative 1. I is what's known as an imaginary number, square root of negative 1. And I squared equals negative 1. So now tell me how we can express this in terms of I. I is, remember, as the square root of negative 1. And also a recommended prerequisite for this video is watching some of my Algebra 2 / pre-calculus videos on imaginary numbers. So, square root of negative 12. So, how can we break up negative 12 into a perfect square number? Well, negative 12 can be written as negative 4 times 3. So basically 4 times 3 is how we write in positive. But then we have this negative square root. So remember, I is square root of negative 1, so we can just break this as negative 2 plus or minus. We're going to have 4 times 3, a product. The square root of 4 is 2. 2 times 2 is 4, obviously. So we're going to have 2i root 3. Because 2 root 3 would be 12. Right, 2 root 3 would be 12 because 4 times 3 is 12. Square root of 4 is 2. And then we leave the other part inside the radical. We have 2i 3 over 2. Now over here we can pull out a common factor. And now we have, this is 1, this is 1, this is 1. So now we have negative 1 plus or minus I root 3 as our two solutions. Plus or minus means negative 1 plus I root 3 and negative 1 minus I root 3. And that's how you would use quadratic formula to solve quadratics. Now let's talk about Diophantine equations. Another type of polynomial equation. Let's try it out. Now, a Diophantine equation is something like x y squared is equal to 14. If I were to ask you to find all possible integer solutions for xy squared equals 14, it's a Diophantine equation. In Diophantine equations, you're usually asked to find all real integer solutions. You might be asked to find all real positive integer solutions. There's many possibilities. Now let's try to find all real positive integer solutions, or all real integer solutions to the Diophantine equation. And I want you to do it. Solve a Diophantine equation. Let's just think about this for a second. We need y squared, we need some number squared times x equal to 14. Let's think of some perfect squares. So we can have 2 squared. 2 squared is 4, but 4x equals 14, that doesn't work out. So let's try 3 squared. 3 squared is 9, but 9 doesn't go into 14. It's not divisible by 14. Like 9 is not divisible by 14. Let's try 4 squared. 4 squared is too big. Well, 1 squared works, so we can have 1 squared. So we can have y equal 1. So if y is 1, 1 squared is 1. 14 times 1 equals 14, and that works out. So we have x is, if we have integer solutions x and y, we might have 14 and 1. Now let's think of another possible integer solution. Let's think of all the factors of 14. You have 1 and 14, 14 and 1. You have 2 and 7, 7 and 2. That's really it. And then you have the negatives. So you have negative 1 times negative 14, negative 14 times negative 1. You have negative 2 times negative 7, and you have negative 7 times negative 2. So you have over here 8 possible integer solutions. Now I want you to find how many of them satisfy xy squared equals 14. Let's just think about this. If we put in a negative 1 squared, negative 1 times negative 1, that's just 1, and 14 times 1, so that works out. But we can't really have a negative as x, right? Because the only way you can have a negative number squared is I, and we're looking for real solutions, so that won't work out. So y has to be positive no matter what, right? Y always, so we can rule out wherever y is negative. Well, y can be negative, my bad, x has to be positive no matter what. Y can be negative, but y squared is always positive. I need to get that straight. Y squared is always positive. Y can be negative, we can have a negative 1 squared, it's always going to be positive. So we have 14 and 1, that works out. Let's try another one. We can have 14 times negative 1 squared. Negative 1 times negative 1 is 1. 14 times 1 is 14. We can have 14 and negative 1. Those are two possible integer solutions. Now, we can't have negative 1 and 14 because that's a square 14. We don't want that. So we can't have vice versa in this case. Now, we can't make 14 negative. These are the only two possible solutions I see. We've tested negative. The only possible solutions we have with a perfect square, another number whose product equals 14, is 14 and 1. Another variation with that would be 14 and negative 1. So the possible integer solutions, real integer solutions, are over here. That satisfies the Diophantine equation. Now I'm going to ask you to try one challenge problem. And by the way, problem credit goes to the Harvard MIT Mathematics Tournament. So this is a problem, an older problem from the Harvard MIT Mathematics Tournament. All problem credit goes to them. Now we have a number that has two prime factors, and we're asked to find them. And I want you to come up with a strategy based off of everything we've learned. You can solve this pretty easily. If you've been paying close attention to everything we've learned throughout the video, I want you to solve the problem, the following problem. Alright. Two prime factors. Well, I think of factoring in this case. I want to break my big number down into smaller factors. How can I factor this? How can I express this in terms of factoring? Well, I see that with what numbers is this number close to? I see if it's close to this number. It's close to close to 8 billion. And 8 billion, well, 8 is a perfect cube. That tells us that 8 billion is a perfect cube. That also tells us that this can be expressed as a difference of cubes. Now this can be expressed as difference of cubes, obviously. Now how are we going to express it like that? Well, this challenge is up to you. I want a challenge for you is to solve this problem. And in part 2 of the Algebra 1 review, I'm going to finish the solution, solve the problem, but I want you to come up with a solution and understand the problem, or at least come up with some ideas to solve the problem. So hopefully this video is helpful, and yeah, it's part 1 of Algebra 1 review, Polynomials.